calculation, calculate the moments. If the slab is square slab, then you may calculate the moment in one direction and repeat that moment in the another direction. But if the slab is rectangular slab, you want to calculate the moment in both directions, that is along L1 and along L2. The formula is m naught 1 is equal to W naught into L1 upon 8, and in another direction m naught 2 is equal to W naught into L2 upon 8. Next thing, you want to distribute that moments into column strip and middle strip. So for that distribution, some basic calculations are required, which are as follows. Basic calculation for external panel problem. First of all, calculate the length of column. LC is equal to given length of column minus overall depth of the slab, flat slab. Then calculate the effective length of column. The first point is total length of column, whereas second point is effective length of column. So for the effective length, if the effective end condition of the column is not mentioned in the problem, you want to assume that the both ends are hinged, and then calculate the effective length of the column. Third is column size, which is already mentioned in the problem. We cannot assume that size. If the problem column size is not given, then the problem is not valid. Third is calculate the moment of inertia for column IC. IC is equal to BD cube by 12. So B is the length of the width of the column, and D is the means B and D is nothing but the size of the column. Then calculate the flexural stiffness of column meeting at joint. Kc is equal to IC upon LE. IC is what? Moment of inertia for column divided by effective length of the column. These are the basic calculation you required. Now second or next step is distribution of moment along L1 direction. If the slab is rectangular, you want to follow this procedure only, means repeat the procedure in L1 direction and L2 direction. If the slab is square, then you may calculate the moment or distribution of moment in one direction and repeat that same moments in the another direction. Okay. Now here we will discuss the rectangular slab, hence distribution of moment along L1 direction. For that you require some basic calculations. First, calculate the moment of inertia for slab. Is is equal to L1 into D cube upon 12, means BD cube by 12 in short. Flexural stiffness of slab Ks is equal to Is upon L2. Relative stiffness ratio of column alpha C is equal to 2 Kc upon Ks. 2 Kc is what? Kc is nothing but the flexural stiffness of column at joint, and Ks is what? Flexural stiffness of slab. Next, relative stiffness ratio alpha S is equal to 1 plus 1 upon alpha C. Alpha C is nothing but relative stiffness ratio of the column. Next, you want to calculate the moment coefficients C1, C2, C3. What is C1? C1 is internal negative moment coefficient, which is calculated by equation 0.75 minus 0.1 upon alpha S. Second, C2 is external negative moment coefficient. C2 is equal to 0.65 upon alpha S, and positive moment coefficient C3 is equal to 0.63 minus 0.28 upon alpha S. What is alpha S? Alpha S is nothing but relative stiffness ratio for slab. So for using that, you want to calculate the C1, C2 and C3 moment coefficients, and then you are able to distribute that moments into column strip and middle strip. Now here see the table. First column is moment, second column is factored moment, third is column strip, and fourth is middle strip. Now we will discuss row wise. First, internal negative moment. So internal negative moment is denoted by Mn, and which is calculated by equation m naught 1, that is moment in L1 direction, multiplied by C1. C1 is the coefficient of moment in negative coefficient of moment. What you get? You get the internal negative moment Mn. This Mn is sorry. Now see, this is Mn. Mn, the internal negative moment. You want to distribute this Mn into column strip as well as into middle strip. Now, as we earlier discussed, the total negative moment, out of that total negative moment, 75% moment is carried by the column strip, whereas 25% is carried by the middle strip. So, distribute that into column strip and middle strip. Simple. M1 is equal to negative moment multiplied by 75% and M negative moment multiplied by 25%. From that you can distribute that moment, negative moment, into column strip, whereas in the middle strip. Second is external moment or external negative moment. So, this external negative moment, how you can calculate? Total moment in L1 direction multiplied by C2 factor, coefficient of moment C2. So, from that equation we get the value of external negative moment. So, this external negative moment is 100% carried by the column strip. There is no distribution in the middle strip for external negative moment. The whatever the moment is calculated, that total moment is acting on the middle strip or column strip only. Third and last point is positive moment. So, positive moment MP is calculated by using equation moment in L1 direction multiplied by C3 factor or C3 coefficient. This is denoted by MP. Now, again as we discussed in the internal panel, the positive moment is acting 60% in the column strip, whereas 40% in the middle strip. So, accordingly you want to distribute that moment. So, positive moment multiplied by 0.6 or 60% of positive moment is acting in the column strip, whereas 40% of the positive moment is acting on the middle strip. That this is the procedure to distribute the moments in column strip and middle strip. Now, this is for L1 direction. You want to repeat the same procedure for L2 direction. Calculate IS, that is moment of inertia for slab, flexural stiffness of the slab, relative stiffness for column, relative stiffness for slab, then C1, C2, C3 factor in L2 direction, and again distribute the moments into L2 direction. After this distribution of moments, you have total 8 moments with you, 5 moments for L1 direction and 5 moments for L2 direction. Out of that, take the maximum negative moment and maximum positive moment and equate that maximum negative and positive moment with MUR max and calculate the D required. Now, what is the checking condition? D required should be less than D provided. If you don't satisfy that condition, then again restart the problem from step number 2. If you satisfy that condition, then go for the shear check. Now, the shear check procedure we already discussed in internal panel. What is the procedure? First of all, calculate the width of critical section dt, column size plus d by 2 plus d by 2. Shear resisted by critical section Vu is equal to total load on the slab minus factored load multiplied by 2 into dt. Calculate nominal shear stress tau V. Tau V is equal to Vu upon Bd. Stress, shear stress in concrete tau C is equal to 0.25 into under square root FCK. Now, what is the checking condition? If tau V is less than tau C, your design is safe. If tau V is greater than tau C, then redesign the slab, means you want to start the problem from step number 2. If you satisfy both the condition, that is for check for depth and check for shear, then go for the reinforcement calculation. What is the reinforcement calculation? Again you want to calculate the reinforcement for reinforcement in longer direction or L1 direction for the 5 moments you have calculated in 7.A step, M1, M2, M3, M4, M5. So, what are that? First of all, discuss longer direction steel. First column strip, in that negative internal reinforcement AST negative is equal to 0.5 FCK upon Fy into bracket 1 minus under square root 1 minus 4.6 into M1 upon FCK BD square bracket complete B and T B and B into D, where M1 is negative moment in column strip and B is the width of column strip in another direction. See, M1 is what? Negative moment or negative moment in column strip, whereas B is the width of column strip in another direction. Assume the bar diameter and calculate the spacing. Provide spacing should be less than 2D. Next, longer direction steel but in column strip, but again external negative reinforcement. AST negative. See, this is not M2, this is M3 and width is in another direction. You are going to calculate the column strip steel, hence use the width of column strip but in the another direction. Assume the bar diameter, calculate the spacing. Spacing should not be greater than 2D. Next, column strip positive steel. See, M4. You are going to calculate the steel in column strip, hence consider the width of column strip, but direction is L2 direction. Assume the bar diameter and calculate the spacing. Spacing should be less than 2D. Now, these are the calculation for column strips, these are the calculation for middle strips here. So, internal negative moment M2, the moment in the middle strip M2 and width of middle strip but in the L2 direction. Calculate the AST negative, assume the bar diameter, calculate the spacing. Spacing should be less than 2D. B positive moment or positive reinforcement. See, this is M5, that is middle strip positive moment, M5 middle strip positive moment. B is the width of middle strip in L2 direction. Assume the bar diameter, calculate the spacing, provided spacing should be less than 2D. Now, we are going to repeat the same procedure for shorter direction. If the slab is rectangular slab, if the slab is square slab, then calculate the steel for single one direction and repeat the same in the another direction. But if the slab is rectangular, you want to repeat the same procedure for shorter direction steel also. And then last but not least, the step is design step. Design steps, the 9 points are most important. First, longer span of the slab, shorter span of the slab, D provided, capital D provided, width of column strip, width of middle strip in both directions, and then reinforcement details. Now, while writing the reinforcement details, as we discussed in the last lecture, you want to write the reinforcement detail in terms of bars at ... spacing. For example, if you use the 16 mm bars at 150 mm center to center, then while writing the steel, you want to write 16 mm Tor bars at 150 mm center to center. This is a right procedure to write. This is the procedure to write the steel in the design summary. Now, from next lecture, we are going to discuss the solved problem on internal panel as well as on the external panels, and then we discuss in the lecture room how to solve the problems or variety of problems. Okay. So, today we will stop here. Thank you.